All right. Moment of inertia. This is a really short section too, so kind of nice after that last section that was so long. Okay, we're going to define mass really quickly as a conceptually as a measure of how difficult it is, how difficult it is to change the translational motion of an object. Hey, wait a minute. How difficult is it to change the motion of an object? Don't we have a definition for that already? Oh, that's right. It's inertia. Okay. Mass is basically a measure of inertia. Okay. Moment of inertia is the same thing, but for rotational motion. Okay. Is how difficult it is to change rotational motion of object. Okay. How difficult is it to get something to rotate or to get it to stop rotating? Okay, that's all stuff that you have to consider when you think about rotational inertia. Okay, now moment of inertia. Moment of inertia of an object depends on the object's mass. Okay, and how far the mass is from the axis. Okay, now that's something important to understand about, like for the slow yo performance task. When you look at the slow yo performance task, you want to create something that has, mass furthest away from the as much mass as far away from the axis as possible, and because that will give you more inertia, which means that it would unroll slower, right? So that's kind of your goal, is you want something that has most of its mass concentrated furthest away from the axis to give it as much rotational inertia as possible, because it will make it harder for it to unroll. Okay. The basic equation is, we use I for moment of inertia, is kmr squared, and k is called the shape constant. Okay, k is the shape constant, and it depends only on the shape of object. Okay. Okay. So some moments of inertia to know, and I don't want to say that you don't need to memorize these. I'm going to say that you should know what these are. Okay. I'm going to say maybe if you memorize them, it's great. I think most of the time you're given the shape constant on the test, or you could solve for it, I guess. I think pretty much all the time it's going to be given to you, though. If you have like a point-sized object, a distance r from the axis, this is like the circular motion lab that you did first day coming back from break. This is going to have a very high amount of a very high moment of inertia, because a lot of its mass is compressed far away from the axis. You have the axis here, this all stuff is really close, but then you have a good amount of mass right compacted at the outside end of the axis. So this is going to just be, the shape constant would be 1, so it would just be I equals mr squared. Okay. If you have a hoop of radius r, so what would happen is the axis goes through the center, and you notice that we have no mass at the center. Okay, it's all located at the radius. All the mass of the hoop is located at the end. So therefore, if the axis goes through the center, all the mass at the end. So this is going to actually have a very high moment of inertia as well. It's also going to be just mr squared, because the shape constant would be 1. If you have a solid disk of where the mass is uniformly distributed and the axis goes through the center as well, okay, then you would notice that all your mass is about uniformly distributed about the axis. You have some out far, you have some out close. Okay, this is just going to be I equals 1/2 mr squared. Okay. Okay, if you have a sphere, this is a sphere. It's supposed to be a sphere. Okay, and the axis goes through the center. So here's, okay. There's your sphere. Okay, and I didn't change colors, which is unfortunate. Okay, you have, like, right, there's your sphere, right? This is I guess I should have drawn that the other way, because that's how spheres are typically drawn, right? Let me just draw. Okay, so it's a sphere. It's a three-dimensional sphere. Okay, axis goes through the center. You notice that again the mass is uniformly distributed, but the only pieces of mass that are furthest away from the axis is right here at the very end. Okay, so therefore it still has it has not so much rotational inertia. So I equals 2/5 mr squared. Okay, for a rod of length L where the axis is through the center, this might be something like your pen or something, or your pen or your pencil that you rotate. Okay, this would be something like this would be I equals 1/12 mr squared. Okay, this one has a really small moment of inertia because again, the only mass that's furthest from the axis is at the very ends of the rod. Okay, and you don't have much mass even in general on here on the rod. Okay. Oh, sorry. It should be ml squared. Okay. And then for the rod of length L, where the axis is through one end, so we're not changing the rod; it's just being rotated about a different axis. Instead of rotating it, around the middle. Okay, if I'm rotating it about the middle, then I'm rotating it like this. Okay, I think you can kind of see that. But if I'm rotating it at the end, that's going to be more like it's hooked on one point on like a hinge, and I rotate it like that. You can kind of see that. Okay. So if I rotate it about that axis, then this is going to change to I equals 1/3 ml squared. And now this one has more rotational inertia because again, you have more mass that's further away. Again, even though this is the only part that's furthest away, this is actually further away from the axis than was on here. Okay, because if you do it through the middle, then you've essentially half that distance. Okay, but now it's all the way on the other end. Okay. Okay, well, there you go. That's moment of inertia. All right, have fun. Gaslight, gatekeep, girl boss.